Chapter 3, Section 3, Lecture, Using Newton's Laws. Remember the essential questions, review vocabulary, and new vocabulary. Cover those before you start reading this. Okay, so what happens in a car crash? Newton's first law, what's in motion stays in motion. If you're driving down the road, and we've all experienced this, and the brakes are slammed, somebody slams on the brakes, you'll get stuff flying up from underneath the seat, or um, if you're not buckled, you'll feel your body keep continuing to go forward, and you put your arms out to stop yourself. This is Newton's first law. What's in motion stays in motion. Now, if you put a seatbelt on, though, and you're wearing your seatbelt, when someone slams on the brake, you're tied down to the seat. And as the seat stops, your body stops. If you don't have a seatbelt on, when the car stops, you'll continue to move forward. Okay. As you can see down here in this picture, this person is in the back seat. They're not wearing a seatbelt. So when the car stops, they're continuing to move forward at the same speed the car was. And that's inertia. Um, airbags. Airbags can also help to slow you down. Okay. Even when your seatbelt's on, if you have an airbag, that will help to slow your body down and extend the time it takes to stop. All right. Newton's second law and gravitational acceleration. Recall that gravitational force exerted on an object is equal to the object's mass times the strength of gravity. F equals mg. M is the mass, G is gravity. You could also put W here, weight equals mass times gravity, but weight is a force, so we're putting in the force here. All right. Basically, what this is telling us here is all things are accelerated towards the center of the earth, all items. And on the picture over here, you can see feathers, and it looks like maybe a pool ball falling through the air. If there is no air resistance, and air resistance, just like if I put a cup on the top of a table, gravity is pulling that cup down, but the table is pushing back up, and that's called the normal force. When a feather falls through the air resistance or that friction in the air pushes it back up. Okay, it's pushing up on it as gravity's pulling it down. The larger the surface area, the more air resistance affects an object. Okay, if I was to jump out of an airplane with a parachute on, before I open my parachute, I'm going to fall really fast. When I open the parachute, I haven't changed my mass. The mass of the parachute and myself are still the same, but I've increased the surface area. I've increased the size of it. The size causes it to have more air resistance and therefore fall slower. So in this case, the reason the feather falls slower is not because it's a different mass, it's because it has a larger air resistance. And that causes it to flow or fall slower. Here's another example. These little grocery bags. If I crumble one up and if I leave one open and I drop them, the one that's open will fall slower because of air resistance. There's more surface area. Okay. Terminal velocity is the maximum speed an object will reach when falling through a substance such as air. In this case, uh, when you set a cup on a table, gravity pulls it down. The cup pushes it up. It's not moving. The forces are balanced. Okay. Terminal velocity is the fastest an object goes. Once this parachute down here, it will only accelerate so fast because of the air resistance. That is the terminal velocity when it's falling as fast as it possibly can. All right. Free fall. Gravity would be the only force acting on the object. The best way to think about free fall is if we go back and we think about Newton's um, experiment, his thought experiment with the cannon and the cannonball. Free fall is it's being pulled down by gravity. The cannonball that is in orbit around the Earth is being pulled down by gravity, but it never hits the surface. Okay, it has enough speed to keep from hitting the surface of the Earth, or enough acceleration, F equals ma. It has enough acceleration to keep from hitting Earth, so it's constantly falling, being pulled by gravity, but it never hits the ground. This causes what appears to be weightlessness. And if you watch the video about the space station and how it works, you'll understand the weightlessness. In this example right here, if the person standing here on the scale and the elevator goes up, as the floor moves up, it's pushing on this person, so they're going to have a higher mass or a higher weight. On this side, where it's moving away from the person, it's falling away from them, it's going to have a lower weight. All right, centripetal force. Centripetal force is that force that holds you in place on this beautiful roundup. They used to call these the roundup. I don't know what they're called now, but at one time it was called the roundup. And you can feel yourself being pushed back against the wall. That is centripetal force. Any kind of acceleration or force in a circular motion is centripetal. Centripetal acceleration, acceleration on a curved path. Centripetal force is that force you feel as you're being pulled towards the center of the object. That's a centripetal force. You also feel this centripetal force and acceleration when this car is going around a corner. Okay, as it's turning around a bend in the road, you feel that centripetal force pin you to the outside wall. Force and momentum, F equals ma. Recall that an object's momentum is equal to its mass multiplied by its velocity. All right. Basically, what we're getting at here is a conservation of momentum. Momentum is always conserved. The law of conservation of momentum. If no external force acts on a group of objects, their total momentum does not change. Here, where we're shooting pool, as the cue ball hits the rack, all right, whatever momentum this cue ball has, when it hits the rack, it is transferred into all the other balls. None of these balls, regardless of what you think, can move as fast as the cue ball, because the momentum of that cue ball is spread out in the rest of the balls here. All right. And that would show how when the cue ball hits, it slows down and all the other balls speed up. The momentum is transferred. Rocket propulsion, we talked a little bit about this in the last chapter. For every force, there's an equal and opposite force. As the gas escapes out the back, it propels the rocket forward. Okay, that's basically all there is to that. For every action, there's an equal and opposite reaction. For every force, there's an equal and opposite force.